Alright guys, welcome to a new video. The topic for today's video is going to be complex numbers. I don't know about you guys, but for me, we did complex numbers in year 1 of IB Math. And so for year 2, we've been doing calculus and the later topics in the curriculum. But this is still on the IB exam. So by the time we finish calculus, we're going to pretty much forget everything about complex numbers. So this is part of review for the HL Math exam. Alright, and we're going to be doing 2 questions, one easy one and one harder one. Alright, and this is the question code if you want to find it online. This question is actually part of a long question. I just took this part because I thought it was important. Alright, so for any complex number z, show that z star squared is equal to z squared star. For IB, the star notation is the conjugate for a complex number. So say complex number is a plus bi, z star, its conjugate, is a minus bi. Alright, so let's try to prove this. Alright, so z star is equal to a minus bi, and z star squared is equal to a minus bi squared, and that is equal to a squared minus 2ab plus b squared I squared, and I squared is negative 1, so this is a squared minus 2abi minus b squared. Alright, now let's do z squared conjugate. So z squared is equal to a plus bi squared, and it's pretty much similar to the top, except it's a squared plus 2ab minus b squared. So let's rearrange a bit into real and imaginary. Sorry, this is a minus a squared minus b squared, and that is the real part, and then we add 2ab, that is the imaginary part. So we take the conjugate, z squared conjugate, and we take the negative of the imaginary part, which is a squared minus b squared minus 2abi, and this is equal to this, equal to z naught squared, and we just proved this. Okay, second question. Let omega be one of the non-real solutions of the equation z cubed is equal to 1. One thing to remember is that complex roots come in conjugate pairs. So there's one real solution to z cubed is equal to 1, and the obvious solution is z is equal to 1. So the other 2 roots are conjugate pairs of each other. Consider, and the second part of the question is, consider the complex numbers p is equal to I is equal to 1 minus 3i, and q is equal to x plus 2x plus 1 bracket I, where x is an element of real numbers. Alright, A, determine the value of I plus omega squared. Okay, so to do this question, we use this equation, z cubed minus 1 is equal to 0, and then we factor. So z minus 1 z squared plus z plus 1 is equal to 0. This is the factoring for difference of cubes, and it's equation that you should remember. Alright, and this is equal to, sorry, not 0. Oh wait, it is equal to 0, but this is equal to this. Okay, and that means that 1 plus z squared. I'm just rewriting this this term is equal to z cubed minus 1 over z minus 1, and then we sub in omega for z, and since omega is a solution to z cubed is equal to 1, that means that the numerator is 0. So 1 plus omega squared is equal to 0. And part 2, 1 minus omega star, 1 plus omega star squared. And since omega is a solution for the equation, and non-real solutions come in conjugate pairs, that means that omega star is also a solution to z cubed is equal to 1. So it is also equal to 0. Alright, part B. Show that omega minus 3 omega squared times omega squared minus 3 omega is equal to 13. Alright, so first we expand omega cubed minus 3 omega to the 4 minus 3 omega squared plus 9 omega cubed is equal to 13. Remember that z cubed is equal to 1 and the omega is a solution, so we can sub in omega cubed into this equation. So this is 1, omega cubed is equal to 1, and 3 omega to the 4 is equal to 3 omega times 1, and we don't sub in for omega squared, and this is just 9 times 1, and that is equal to 13. Okay, so let's clean this up a bit. 10 minus 3 omega minus 3 omega squared is equal to 13. So we break 10 into 13 minus 3, and this is minus 3 omega minus 3 omega squared is equal to that. And we had 1 plus omega squared is equal to 0. We proved that in the previous question. And we can and this is 13 minus 3, 1 plus omega squared. So that is just 0. And then so this is just 0, so we just cross it out. And we get 13 is equal to 13. And left side is equal to right side. So we prove this equation. Alright, part C. Find the values of x that satisfy the equation absolute value of p is equal to absolute value of q. So for complex numbers, this notation, let's say z is a complex number, and z is equal to a plus bi. Complex numbers are kind of like a vector where the absolute value sign means that you take the scalar of the complex number, and this is what that notation means. From above, we have p is equal to 1 minus 3i, and q is equal to x plus 2x plus 1i. Alright, so scalar of p is equal to 1 squared plus 3 squared plus negative 3 squared, and that is just root 10. And for q, this is equal to x squared plus 2x plus 1 squared. And we can equate these two because they're asking us to solve that. So 10, so we square both absolute p and absolute q because they're both square roots to get this equation, x squared plus, let's expand this term, so 4x squared plus 4x plus 1 Alright, so 5x squared plus 4x minus 9 is equal to 0. Okay, so that means, so we can factor this. 5x, x, and the second term multiplies to negative 9. Two numbers that multiply to negative 9 and add up to the positive 4, positive 9 and negative 1. And that is equal to 0. So x is equal to 1, or x is equal to negative 5 over 9. That is the x values that satisfy this equation. Alright, D. Solve the inequality real of p times q plus 8 is less than imaginary of p times q squared. So for a complex number z, that is equal to a plus bi, real of z is equal to a, and imaginary of z is equal to b. And that is just a notation of these two functions. Okay, so now we need to solve for pq, and we need to do some multiplication. Alright, 1 minus 3i x plus 2x plus 1 I, and we need to expand these terms out, and we get x plus 2x plus 1i, and then minus 3xi. I times I is negative 1, and this is negative, so we get positive plus 3 times 2x plus 1. Alright, let's expand, let's combine into real and imaginary parts. So x plus 6x plus 3 plus 2x plus 1i minus 3i. Okay, let's combine. This is equal to 7x plus 3, and this is equal to 2x plus 1 minus 3. So 2x minus, oh sorry, this is 3x. So this is 1 minus x I. And they want us to solve real of pq, which is 7x plus 3 plus 8 is less than imaginary pq squared, and imaginary is 1 minus x. Okay, let's try to solve this equation. So real 7, so this is the second part. 7x plus 3 plus 8 is less than 1 minus x squared. So let's expand this out. 7x plus 11 is less than x squared minus 2x plus 1. We bring everything onto one side. X squared minus 9x minus 10. And we can factor this, and we get x minus 10, x minus x plus 1, sorry. And that is, we solve this for equal to 0, and then we do interval tests to see when the quadratic is greater than 0. So the function is 0 at x equal to 10, and x is equal to negative 1. And since this is a quadratic, we don't actually need to do interval test, because we know that this is positive, because the leading coefficient is positive, so it opens upwards like this. If the leading coefficient of x squared term is negative, then it would look something like this. Okay, and we know that it is 0 and negative 1 and 10. So it is positive for this section and this section. So it is greater than 0 when x is less than negative 1, and x or x is greater than 10. And that is the answer to this question. Alright, that is the last question. Hope this is some good review for imaginary numbers, and it's also a bit of a review for vectors since a lot of the concepts, some of the concepts are similar. Alright, thank you for watching. Bye.